Okay, so we are going to focus on sine and cosine for the next few days. And then after we graph sine and cosine, I'll teach you how to graph tangent, secant, and cosecant. Okay? We won't graph cotangent. Okay, so we're going to focus on y equals the sine of x first. Okay? Y equals the sine of x. So x, that's our independent variable. What kind of values are we plugging in for x? We're plugging in angles, correct? And if we plug an angle into the sine of x, then our output will be some sort of ratio, right? So if we think about our unit circle and we think about the special values, we know that the sine of 0 is 0. And the sine of pi over 6 is 1/2. And the sine of pi over 4 is radical 2 over 2. And blah, 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 blah. The sine of pi over 2 is 1. Okay? So we start at 0, we reach 1, and then what happens to our sine values? They go back down until we have a sine of 0 again. Right? Well then, once we get past pi, our sine values dip down into the negatives, all the way down to -1, right? And then our sine values, we rotate back until we're at 0. Okay? Now, are these the only 16 points on the unit circle?
No.
Okay, there's an infinite number of points. We just don't talk about them because they're not special. Okay? But if we take all of our outputs from any angle input for the sine, this is what would happen. I have a little demonstration for you. Are you ready? Okay. Okay, so here, do you see how we go around the unit circle? And as we go around the unit circle, it plots the outputs. So the sine of 0 is 0. The sine of pi over 2 is 1. The sine of pi is 0. The sine of 3 pi over 2 is -1. And the sine of 2 pi is 0. Isn't that fun? It's bothering you. What bothers you?
Just the way it moves. He's mad he can't look at both of them at the same time.
Now, if we continue to rotate around and around and around and around and around our unit circle, this pattern is going to happen over and over and over and over again. We call this a periodic function because we keep repeating and repeating and repeating. Some people might call it cyclic. Okay, we do the same thing over and over. Okay, so what does this remind you of?
Roller coaster.
Waves, roller coaster, waves. In physics, do you talk about sound waves?
Yeah.
What kind of looks like, right?
Yeah.
Okay. So here is what the sine of x looks like. What I'd like you to do is go ahead and draw this graph, but only the red piece. Or if you want to draw all of it, highlight the red piece because that's like one unique portion of the graph that we're going to talk about. But we know it goes on forever in both directions. Pay attention to the marks that I make on the x and y axis. Those are the important x and y values. make sure when you draw your curve it's nice and smooth, there's no corners. It should also have a little bit of symmetry. Now, what letter does this resemble? I would probably be more inclined to say S just because it's curvy. It's like a backwards S, right? Like a backwards S. Okay? So I think it has a similar shape to an S. It might not be oriented the same way. And this is the sine graph that looks like an S. Okay. All right, now, when we go back to the unit circle and talk about y equals the cosine of x, does the cosine outputs resemble the sine outputs? Okay, they just go in kind of a different order, don't they? Okay. If we look at our outputs for y equals the cosine of x, like the cosine of 0 is 1, right? And then our cosine values fall until we're at the cosine of pi over 2 is 0, right? And then we rotate until, right, we have negative outputs now for cosine, all the way until the cosine of pi is -1. And then our cosine values start to increase, right? We rotate, we're still negative, but we rotate all the way up to the cosine of 3 pi over 2 is 0. And then we have positive values again until we're back to the cosine of 2 pi is 1. Okay? I can point those out all I want, but I think it makes a lot more sense when we're looking at that image that Dallas doesn't like. Okay, so here's the same thing. Now we're going around the unit circle and we are grabbing the cosine values. Okay, the cosine of 0 is 1. The cosine of pi over 2 is 0. The cosine of pi is -1. The cosine of 3 pi over 2 is 0. And the cosine of 2 pi is 1. And as we continue to rotate over and over and over and over and over again, this will keep happening. Right? So when we look at just the one piece, we can tell a big difference between sine and cosine. But if we continue to draw as much of the cyclic behavior as we can, they look a lot the same, don't they? Okay? They're going to have a lot of the same properties. We're just going to start our drawing a little bit differently. Okay? So let's highlight that specific piece, the unique piece of the cosine graph. Okay, here's y equals the cosine of x. Once again, this red portion is that unique piece that we'll talk about, but then we know that it's going to go on forever. To me, it looks like you're kind of drawing a valley. Okay. So once again, pay attention to those x and y. The y coordinates, I would really focus on the 1 and -1, and then these x marks here for those 5 coordinates. Those 5 coordinates are going to be really important whenever we have our next lesson. Is that Wednesday? This one's a little bit more difficult to draw smoothly and symmetrically. I'll take some practice. Okay. So what we're going to focus on today are some of the properties that a sine and cosine graph have, and how we can identify the values if we're looking at an equation. Okay? If I give you y equals cosine of x and y equals sine of x, you can give me this picture. But what happens when we start adding numbers to the inside or the outside of the function, like we talked about in chapter 1 with our transformations? Okay? That's what we're going to focus on today. So first, let's talk about a couple characteristics of the graph. The first is called the amplitude. Okay? Now, when you hear the word amplitude, I want you to tell me what you think of.
Guitars.
Okay, and why would a guitar have an amp?
Amplifiers to make it louder. Something like that.
Okay. Louder versus quieter. Okay. So tell me about sound waves. Sound waves that are loud, what do they look like? They're really big, right? Sound waves that are quiet are really tiny, right? So what do you think the amplitude is referring to when we talk about our sine and cosine graph? Okay, the height of our waves. Okay? So the amplitude is actually, it's not the total height, it's half of the total height. Okay? It's basically the height from the middle of the graph up or the middle of the graph down. These bounce up and down. Okay, so let's look at our sine and cosine graphs. What is the total vertical distance? Our total vertical distance is 2. We bounce from -1 to 1. So our amplitude would be would be 1 for both of them. Okay? Since we bounce from -1 to 1, we have a total height of 2. Half of that is 1. Okay. The period. Amplitude refers to our vertical height. So period is going to refer to what characteristic about a graph? Our horizontal length. Okay? So before you start writing this down, you know how our graph repeats over and over and over and over? Okay, we say that the period is the length before we start repeating the graph over again. Okay, so like we drew an S for our sine graph. That was the one period because then we would draw another S and another S and another S. Okay, so go ahead and write it down. That horizontal distance before we start repeating. Okay, so go look at your graphs. highlighted is one period, because then we start to repeat the process. So what is our horizontal distance before we start to repeat? Say it louder, Addie. 2 pi. The period of our, what we call parent functions would be 2 pi. If we go back to our sine graph, okay, here we draw an S. From here we would draw that same pattern again. So one unique piece of our graph, we call it one period, has length 2 pi. Okay? So our parent graphs have amplitude 1 and period 2 pi. We're going to use those numbers to help us. Okay? Now, the chance of me asking you to graph one of these two graphs as a parent function are like slim to none. Okay? What I'm going to ask you to do eventually is graph things that have been stretched vertically, horizontally, shrunk vertically, horizontally, and even shifted all around. Okay? So, we are going to talk about graphs that look like this. Please write down at least one of these, okay, so you can identify the A, B, C, and D. They affect sine and cosine the same, so you really only need one, but feel free to write down 2 of them. Bless you. Okay, what do we talk about that number in front of a function? A number in front of a function, like if we were talking about x squared, 4x squared versus 1/3 x squared. What is that number multiplied out in front? How is that affecting our graph? Stretching, which way did you say, Dallas? Vertical or horizontal vertical stretch or shrink. Sorry, that's what you said. Vertical stretch or shrink. What is that going to affect on our sine and cosine graph? The amplitude. Okay? So that A is going to give you the amplitude. Now, why would I put absolute value there? Okay? Amplitude has to be positive, but is it possible that A is negative? Okay? What happens to a parabola if A is negative? It reflects. Okay? So we need to keep that in mind. If we have a negative A, then our graph is going to be reflected about the x-axis. Okay, so our cosine is going to look like a hill instead of a valley. Okay? Or the sine curve would dip down first instead of up first. We'll talk more about that on the day that we actually graph these, but I am asking you to identify if you have a reflected graph or not. Okay. B is multiplied inside of our function. If we have a number multiplied inside of our function, what is that going to affect? A was a vertical stretch or shrink. What's B? Horizontal stretch or shrink. And horizontal stretch or shrink is going to affect the period of our graph. So our parent functions have a period of 2 pi. That's what we're going to base everything on. So to calculate the period if B is something other than 1, this is what we're going to do. Okay? The period is going to be 2 pi divided by B. Okay? That will tell you the length of your new period, taking into account that B is a horizontal stretch or shrink. Okay? A nice straightforward way for you to handle it. Okay? Now, if we come up here to C and D, we know that those are going to affect our graph as a horizontal or a vertical shift, right? C is our horizontal shift, D is our vertical shift. However, do you remember that if we have a number multiplied to x, that's going to affect our horizontal shift. Okay? Remember when I made you factor it out so you could see the correct shift left or right? We're going to have to do the same kind of thing. So we're going to identify what I call a starting point. That's where we are going to start our frame when we get to graphing them next week. So the starting point of our frame is going to occur at C over B, comma D. Okay? The D is obvious as a vertical shift up or down. But since that stretch horizontally is going to affect our horizontal shift, we are going to have to use both C and B to figure out that horizontal shift. Okay? All right. So I have 4 examples that we're going to go through. Okay? First 2, nice and simple. The second 2, they're not difficult. They're just not as simple as the first 2. Okay? So we'll start off simple. Y equals 4 sine of x. Y equals 4 sine of x. Kaya, what is our A value? 4. Our A value is 4. Okay? So, Emily R., what does that tell us?
That it's stretched like a distance from like halfway to 4.
Okay, yeah, and we describe that as our, good. So our amplitude is now 4. This sine graph is going to be a lot taller than our original function. Okay. The coefficient of x is our b value. Everybody, what is our b value? 1. Okay, so we don't have anything that's going to affect the period. The period is always 2 pi over b. Well, if b is 1, then our period is still going to be 2 pi. SP, starting point. Are you okay with me abbreviating? Okay. So then our starting point is the shift. Okay. Is there a C value? Is there a D value? No. So just like our parent functions, we are going to start at 0, 0. Okay. Like I said, our starting point is going to be where we draw what I call a frame. We'll get to that in our next lesson. Okay, but I just ask that you identify it first. Okay. All right, let's step it up a notch. Yeah, write this one down. Y equals negative 3 cosine of 2x. Okay, so our amplitude. Okay, Riley P, what would our amplitude be? Ooh. Notice how Riley said 3 and not negative 3. Okay, good job, Riley. Amplitude's always positive, but that negative, Austin, what does that negative tell us? Good. So our amplitude is 3, but I'm going to make a note that this is going to be a reflected graph. So instead of a valley, it's going to look like a mountain because it's going to flip upside down. or I guess more of a hill. But we'll talk about that more, like I said, in our next lesson. Okay, let's calculate the period. The period we calculate by taking 2 pi divided by b. We take 2 pi divided by b. Okay. Nate, what would our b value be? It'd be 2. So 2 pi divided by 2 is pi. Our period is pi. So what's happening is the cosine is being drawn in a shorter amount of time. Okay, so it's going to be more squished horizontally. Do we have any shifts? Like left, right, up, down? Okay, we don't have a minus c and we don't have a plus d, so our starting point is going to be 0, 0. That is not where our graph starts, it's where our frame starts. We'll talk more about that. My Algebra 3 kiddos, did you guys do the framing method? Yes. Where you like draw a rectangle and then draw it in? Okay. All right, let's step it up a notch. Write down number 3. Okay. Everyone, all together, what is our amplitude?
2.
Thank you to the side of you. So I can hear.
Yeah.
Our amplitude is 2. Our period is 2 pi divided by b. What? Our b value is 2. So Monique, our period is pi. Okay, so there's A, there's B. Okay, now we need to calculate our starting point. Okay, now our starting point, I'll do this a little bit backwards. What's the y value of our starting point? Okay, this right here is our d value. It's -2. Okay, now the x value of our starting point, we have to do a little bit of work for. Remember, the x value of our starting point is c over b. Okay, well, our c value is right here, pi over 3, divided by our b value right here, which is 2. Okay, now look back at that form. Look at how it is bx minus c. Remember, if we're subtracting in sign, we have a shift to the right. So I'm going to keep this as a positive pi over 3. And if we take pi over 3 divided by 2, that's the same thing as taking pi over 3 multiplied by 1/2. Dividing by 2 is like multiplying by 1/2. So our starting point is pi over 6, comma, -2. Yeah, that works. Questions about how we got pi over 6? At your table, I'm going to give you 2 minutes to work together on this one, and then we'll check our answers. Work together, so I should hear some voices.
It's divided by. It's divided by 1.
All right, let's chat. Your 2 minutes are up. Pod 1, what did you identify as the amplitude? That's MND. Good. Pod 2, anything to add to that? It is reflected. Okay, pod 3. What did you identify as the period? 4 pi. So 2 pi divided by b is 1/2. 2 pi divided by 1/2 results in 4 pi. Pod 5, what did you get for the x coordinate of the starting point? Pi over 3. How did you get pi over 3?
That is pi over 4 divided by 1.
So if we do pi over 4 divided by 1/2, pi over 2. Like this? Mary Kate, like that? Like this?
Yeah.
Pi over 2? Okay. Pod 6, do you agree with pi over 2? Pod 6 says it's negative. Since we're adding inside is a shift to the left, so it does need to be negative. This is bx minus c. So since it's a plus, we have to do the opposite. Okay? And then pod 7, what is your d value? Pod 8, how does everything look? Do you approve? Okay. On Monday, we're going to do the practice ACT test. Okay? Your homework needs to be completed by Monday. Does anybody have their radiant snowman? I'm going to decorate my walls. Does anyone have theirs to turn in? If you didn't pick one up and you'd like to color one for me, there's some right here for you. Okay?